send it down.
Yeah, you can probably do it to your field also.
Yeah. Okay.
So welcome the rates from Colorado State, where it was speaking numerical methods for parameterized basis for polynomial systems. So,
thank you, Alexei, and thank you for the invitation. Thank you all for coming today, and Chi, I look forward to our talk tomorrow. Yeah, so I'm here from CSU. I'm here to talk about my little corner, one little corner of numerical algebraic geometry. I guess John Hanstein was here maybe 6 weeks ago or so. We talked about real solving and real numerical algebraic geometry. So it's another little corner. There are lots of other little corners that we can talk about if you're curious later on. But for now, I want to focus on parameter spaces. This is something I got interested in several years ago. There are a few algorithms in numerical algebraic geometry, a few main algorithms, and I kind of I came to the realization that this is one that comes up a lot with applications, and I like applications. So I'll talk about this. Feel free to stop me if you have questions, of course, along the way, and we'll go from there. Okay. Can you guys see this okay in the back? I don't know what we do about it otherwise. So this is my long-term vision for this little piece of numerical algebraic geometry. The goal, this is a computing seminar, right? So the goal anytime you're computing is to satisfy the needs of the user, whatever that user might be, right? Whoever that user might be. In my mind, for this talk at least, and for this piece of the world, is some researcher in some discipline with a parameterized polynomial system asking some sort of question about the parameter space. So here's a problem that comes with some parameter space built in. Now I want to know, how many points do this, or over which points something particular happens, or how many chambers are there, whatever that might mean. And I'll mention that later. So ultimately, you want to have software that you can just dump a problem into, and then maybe there's a little drop-down menu of questions that you could ask, and you ask a question and you hit go, right? I mean, that's sort of the dream. That's what you'd like to do. That's not where we are now, but that's what we'd like to aim for in the long run. So which methods should be implemented in this sort of software? Of course, whatever works. People want fast answers, and hopefully they want reliable answers. As you're coming up through numerics, I'm very much on the numerical side of the numeric symbolic computing seminar. Sorry for that, for those of you who really love the symbolic side and hate the numerical side. I like both sides, but today I'm talking about the numerics because that's more of what I'm used to. So people who grow up in numerics, there's always this push to be faster and faster and faster because, of course, oftentimes that's the value of numerical computation, at least sometimes, over symbolic computation. But then you have to worry a little bit about reliability. Right? You have to worry that you're getting the right answers or something close to the right answers. So Agnes Santo came, I guess, last fall and talked about certification. So if you want to know more about that sort of reliability, about certification, you can go back and watch her talk sometime. And what software should be out there for users? There are a few options now that each do a little bit, but nothing that does as much as I'd like it to do. So again, whatever works. I've worked on Bertini for a lot of years, and I'll talk more about Bertini later. So I like that sort of computation. I like that software package, but whatever works. The goal of this isn't until the end, isn't to talk much about Bertini or about particular software. It's about algorithms. Okay, so that's sort of my long-range goal, and it's something that I'm sort of gearing up for over time here. Today, I want to talk about a few particular problems where there are parameterizations or parameterized polynomial systems. So I want to introduce a few problems in a very sort of high-level way. I'll say what the problems are. I'm not going to write any systems on the board. I'm not even sure. I have them all somewhere, but I probably couldn't reproduce them off the top of my head anyway. And then I'll talk about some techniques that have been developed to solve those particular kinds of problems. And they aren't the final answers for any of these problems, but it's progress. Okay. So it's very much an overview, sort of a survey talk. But if you want more details, just ask. So a few caveats. The lists of problems and the list of techniques aren't even close to comprehensive, especially the list of problems. Just throwing some ideas out there to show you kind of what we can do right now. There are different meanings of parameter space. Sometimes we care about real points, sometimes we care about complex points. Sometimes we care about real solutions, and sometimes it's okay if they're complex. Sometimes we work over finite fields. I never work over finite fields. I use floating point numbers, and it's hard to do a lot of to work over finite fields with floating point numbers, at least in my experience. So there are different meanings. Sometimes I mean a whole Euclidean space, and sometimes I just mean a proper algebraic set inside a Euclidean space. And again, today we focus on numerical methods. I noticed that there was a talk last February, so a little over a year ago, about symbolic methods for parameterized polynomial systems. So, so if you want to know more about that, you're disappointed by my talk, then you can go watch Robert Lewis's talk. Okay? Okay, so here's my game plan. Like I said, I'll give you several applications. I'll go over homotopic continuation. You've had a few speakers about homotopic continuation, so I don't want to beat this to death, but I'm willing to talk about it as much or as little as you'd like. So I'll say a little bit, and then I'll wait for a few seconds to see if anybody wants to ask more. And then I'll go over a few techniques. So this is the core of the talk. So fiber products, if you want to find points in parameter space where the dimension of the solution set is different than the general dimension, fiber product method will be useful, or could be useful. We'll get to that when we get to it. John Honstein and one of his undergrads, Zach Griffin at Texas A&M several years ago, developed something called a gradient descent homotopy. I'll talk about those a little bit because I think that's a cool idea that hasn't been used a lot yet. And then I'll talk about some software that was developed at CSU, parametopy, which is useful in a different sort of way. And so we'll get to it when we get to it. We sort of start with the more highbrow algebraic geometry stuff and work our way down to the lowbrow brute force kinds of techniques. So, then I'll say a few words about Bertini 2. I'm traveling on a Bertini 2 development grant, so I should say a few words about that at least. And then a few other announcements about upcoming conferences and things. Okay, so applications. So there's this fairly well-known problem of Steiner to find, and it's been known, the solution's been known for a long time, to find the maximum number of real plane conics, or the given 5 real plane conics, or 5 plane conics in general, how many plane conics are tangent to all 5 of those? And the answer in general is 3264, or 3,264 ways maximally of finding a conic that's tangent to 5 given conics. And then Fulton asked, if you make them real plane conics, can you find 5 real plane conics such that there are 3,264 real plane conics tangent to all 5 of those? So you set out your 5 plane conics, and then you want to find every conic that you can that's tangent to all of those. And 3,264 is the proper number. It's the maximal possible number. So that's Fulton's variant on Steiner's problem. So the goal, to translate this into the world of polynomial systems, the goal is to find a real point in some particular parameter space above which there are 3,264 solutions, 3,264 real solutions. So we can write down some polynomial system. We want to know what the coefficients are for that polynomial system. I'll leave it at that. What coefficients there are that will give you 3,264 real conics that are tangent to all 5 that you started with. That gave you the polynomial system. So it was solved by Fulton, apparently. This was unpublished, though. So later it was published by some people. There are references at the end, and then confirmed numerically by this paper, Griffin and Honstein. So if you want, you can go to Griffin and Honstein. This is where I learned about this problem, in fact, and read details about the history of the problem a little bit and about their technique. But I'll talk about the technique in a few minutes. So that's the first. There are 4 of these. There are a total of 60 slides, by the way, in case you're keeping track. All right, Stewart-Goff mechanisms. So this is a platform mechanism, and the idea is if you build it the right way, you can tip the platform with 2 degrees of freedom. And so this is good for things like flight simulators. Things like telescopes are often put on Stewart-Goff platforms. So a general one of these will have, so if you don't build it in a particular way, if you fix all the leg lengths and make other certain assumptions, if you write down a certain kind of Stewart-Goff platform, you end up with 40 complex assembly modes. So 40 different ways you could build this thing with those fixed leg lengths. So the question then is there a choice of leg lengths so that all 40 of these are realizable, so that all solutions are real. So you can actually physically realize all 40 different configurations. So the theorem is, in general, there'll be 40 complex, but we somehow want to move around in parameter space to find the ones that have the most real solutions that we can, the most real configurations. Same goal as before. We want to move around in parameter space and find as many real solutions as we possibly can. right? So we want to move around parameter space, and as we move, the number of complex and real solutions can vary, right, over time. So again, this was solved by Dietmeyer back in '98, and then again confirmed numerically by Griffin and Hanstein in '15. Same technique, so I'll talk a little bit more about that in a little bit. So there's both an algebraic geometry-oriented problem and an engineering problem. Here's another engineering problem. So given a particular kind of mechanism, so Stewart-Goff is one of them, but there are many other kinds of mechanisms out there. My friend at General Motors I work with, Charles Wampler, always tells me a door is a mechanism. There's a joint, and it goes back and forth, right? There's a fixed part and a part that moves, and so it's a mechanism. Not a particularly exciting one, but still, it's a mechanism. So given a particular mechanism type, find all examples of that particular type having exceptional mobility, meaning that if you build it with just the right lengths and just the right sizes, instead of being fixed, it'll tip, right? So there's an example of this where you take, it's a Stewart-Goff platform again, and so you have you have the floor, and you have a platform up here, and you have 6 legs coming down and attaching to the floor. And if you make this an equilateral triangle and the bottom an equilateral triangle pointing the same way, and get the leg lengths just right, it'll spin down like this and then lift up on the edges. There are illustrations of this on Charles Wampler's website. So it moves in an unexpected way. It's the sort of thing where if you're going to build this mechanism and you're expecting it to be a table, and then you build it and you put a glass on it and it spins down and flips over, that's not a good thing. So it's good to be aware of these for good reasons and for bad reasons. So, I mean, you want to avoid that situation, but at the same time, sometimes people want exceptional mechanisms because they have more constraints than they seem like they should, and so sometimes they're more robust. The mechanisms that get built are more robust. Something can break, and it'll still have some mobility in it, and not unintended mobility. I mean, if the hinge breaks on the door, there's unintended mobility. That's not good, right? We didn't keep the mobility that we'd kind of like to keep. Okay, so what's the problem here, the mathematical problem? We want to find all points in some given parameter space at which the dimension of the solution set of the polynomial system is greater than that expected. So with polynomial systems, parameterized polynomial systems, for a Zariski open set, so almost every point in the parameter space, you have the same number of solutions. But over a thin set, over a measure 0 set, you'll have possibly different dimensions popping up and possibly different numbers of solutions. And so we're after these little tiny sets, and we somehow wanted to find these. So this is actually the first thing I'll talk about, the first technique I'll talk about. We have an algorithm that works, an algorithm that theoretically works, and in practice it works really well for very small problems. And so we're working on making it more efficient now. So I'll talk about that one. That's actually the first technique I get to, Fiberproducts. Okay, and last of the 4 applications, chemical reaction networks. Given some chemical reaction network, you can write down the chemical equations for this and easily translate them into a polynomial system. There are a number of places you can read about this. I can tell you about it more later if you're curious. The question now is, can you find points in parameter space, typically positive real values, because these typically, these parameters that you're dealing with in this kind of problem are physical quantities, so you want them to be real, of course, and you want them to be positive generally, or at least non-negative. So can you find points in this real parameter space at which the solution set has surprisingly many solutions? And the solutions in this case, for this kind of polynomial system, in the application correspond to stability. So you want to find points, not stability, sorry, but stationary points. You want to find regions of parameter space where there are multiple points where the reaction is stopped, right? And for a lot of reactions, there's only one sort of stable point, or one steady state. The reaction churns and then it stops at the end. But for some sorts of chemical reaction networks, there can be multiple steady states. Okay, so here again, we kind of want to fish around in some parameter space, right? Fish around and try and find some points that are special somehow. And some work's been done on this, and this is where parametopia comes in. That's the third thing I'm going to talk about today, the third technique. But the problem is still very much open, and we've only approached really one chemical reaction network with this. Others have worked using algebraic geometry actually in other chemical reaction networks, other problems, specific problems. I'm not going to talk about that today, but it's out there. So I can tell you more and give you some references later if you're really excited about that. Okay. questions yet? All right, cool. So, next up is homotopy continuation. Have you guys seen a lot of homotopy continuation? I don't know. Alexa, I guess you've probably been at all of these talks, so. It depends. Okay. All right. Well, I'll say a few words at least. So, this is the main technique in numerical algebraic geometry. Almost all algorithms in the field boil down to homotopy continuation, at least in the part of it that I work in. So here's the problem in general. If you want to solve a polynomial system, f of z, so this is where we have several polynomials and several equations. So so z is several variables, excuse me. So if you want to solve this thing, what we do is we build. So we call this a target system. We build a start system, g of z, same number of equations and the same variables, right? And it's somehow built so that it looks like f. Maybe the degrees of the g's are the same as the degrees of the f's. That's the simplest one. It's also the least efficient for solving oftentimes. There's a whole yoga to how to build good g's for different f's. And there's a whole stack of options. I mean, so there's the simplest thing that I just said that we can write down in a split second in a computer, and then there's an extremely complicated thing that takes a very long time to write down for a lot of problems, where you can build a really sophisticated G, but then the work that comes after that is much easier than the work in the simplest one to build. So it's a question of whether you want to pre-compute or post-compute. So anyway, we start with f, we build G, and we put them together into a homotopy function. So we throw in a new parameter t, and when t equals 1 in this homotopy function, we've got g of z equals 0 more or less. We just throw in a random complex number, which I can tell you about if you care. It's called the gamma trick. But in any case, when t equals 1, this term dies, and we have just g equals 0, and that's the system that we started with that we know how to solve. Right? So we know all the solutions there, and then we vary t from 1 down to 0, and then this term is dead, and we have just f left over. And so you start with the solutions at g, and then you morph over into f, and your solutions come along for the ride. And there's some algebraic geometry that says this is cool. You don't have to worry about anything. In fact, numerically you have to worry about some things, but that's for me to worry about. Hopefully not for you guys. Okay, so here's a schematic. This is the way you can at least picture some of it. So at t equals 1, these are the solutions of g. So we have 4 solutions here. And at t equals 0, these are the solutions of f. There are just 2 over here. And we're going to move t from 1 to 0, and we'll get that the solution varies along the way. Okay? In fact, t is complex, and we move through complex space in a particular way. And there are finitely many points above which these curves can go off to infinity. But if you choose a random path through parameter space, through t space, you won't hit those points with probability 1. So again, there's sort of a Zariski open statement here. Sort of one. It really is a Zariski open statement here. There's a measure 0 set that you want to avoid, and you're going to avoid it with probability 1. Okay. So, so this solution, the third one, connects to the first one over here. It can be that multiple solutions at t equals 1 connect to the same solution at t equals 0. That would just mean you have a multiplicity 2 solution over here. And it can be that you have extra solutions over here that correspond to solutions at infinity. If we work over projective space, we close things up at infinity, this would wander off to infinity over there. Or if we work in affine space, we can just truncate any paths that get above a certain norm. But in any case, that's the schematic. That's generally how these things look. You start out on a certain number of paths, and if you've built your homotopy function correctly, that's not a hard thing to do, and you've tracked your paths correctly, that's a slightly harder thing to do, but hopefully the software does it well, then you should end up with all of your solutions over here, and some paths that went off to infinity. And if you're working over complex projective space, maybe you care about those solutions too. With the people I interact with, they often don't want to think about that. Okay. So, sorry, when I say the people I work with, I mean the engineers and scientists. They often don't care about what's at infinity or what's in complex space. But the algebraic geometers I work with, of course, do. So how do you track a path now? I mean, Z could have, say, a dozen variables. It could be a dozen variables. Or, we've tracked paths where there are 3,000 variables. We don't find all solutions in that case, but we can track paths in that case at least. So this is this little line segment represents however many dimensions you want. Right? It's not just one dimension. This is the z direction. So this could be have several hundred dimensional, and this is one dimensional, so we can't just trace it with our finger. Instead, we know the starting point. We have the polynomial system, the homotopy function that defines the path. And so we can use something like Euler's method to predict, move along the tangent direction just a little bit. So we go off the path a little bit, then freeze time, freeze t, and run Newton's method and correct back, right? And that's the, I'm saying sort of the most vanilla version of this that there is. We do other things than this, but that's roughly how it looks. Schematically, that'll work. And we just do that all the way across. In fact, we don't actually do it all the way across. But again, I'm just sort of saying the simplest thing. And the idea is, after doing this, it's just linear algebra, just numerical linear algebra to walk along these paths. And we do that starting at each path. And of course, if you have 4 paths and you have 4 processors, you can drop one path on each processor after a little bit of startup time. And then you can track all the paths and the time it takes to track the worst of the 4 paths. Things get funky when paths get close to each other. The Jacobian matrix, well, when they actually touch, goes singular. That's bad news for linear algebra. When it gets close, then it becomes ill-conditioned. That's bad news for numerical linear algebra. So there are things to worry about, but a lot of that's automated away in the software. In fact, that's a lot of what I've been thinking about more recently than this stuff. Okay. So yeah, you see many details. In fact, you change step length along the way. I mean, if you've seen ODEs before, this is probably not new to you. Something that's kind of special to Bertini, something that was in my thesis back in the day, was that we change precision along the way. So as you do come into this case where paths come very close to each other and the conditioning gets worse, we approximate the condition number, and that gives us a signal that we need to increase precision. And so
how does precision come into your system? I mean, is it big float or what?
Yeah, so we start with doubles, and we use this library called MPFR that lets us use arbitrary length.
Right from the start, you use MPFR?
Well, we start in just C double, and in fact now in the redevelopment of Bertini, I'll talk about later, we use C++, in fact boosts double, and so. But we start in the sort of the native double that works on the hardware as fast as possible. And then when necessary, we switch over to MPFR and increase precision as we get closer and closer to singularities. And then we keep monitoring once we're past the singularity, and when it gets low enough, we just jump back to double. So in fact, right now, the way Bertini is written is there are sort of 2 versions of Bertini. There's a double version, double float version, and an MPFR version. And we have ways to jump back and forth between the 2. So there's sort of a 3rd version that calls those 2 as necessary. Does that answer your question? Okay. It's very clunky the way it's implemented right now.
Once you jump over to the big float version, you slow down a lot, right?
Yes, there's a huge slowdown, because that's all in the software. That's not supported in the hardware. And so, we see something like a 30 times slowdown once we have to jump to MPFR. Yeah. So, I mean, it would be much better to stay away from ill-conditioned zones completely. That's something that one of my grad students and I are working on now. But, we're working on it. Okay. So that's adaptive step length, adaptive precision, and in fact, as you're coming in towards the end, with probability 1, paths won't collide with each other along the way, but they can collide at the end because you might have multiple solutions to your polynomial system that you want to solve. You can't get away from that one. That's what you want the solutions to. So, given that things can get kind of nasty near singularities, they're super nasty at singularities, but given that they start getting nasty numerically when you get in the vicinity of a singularity, we play all sorts of games where we extrapolate to t equals 0 without actually walking into it. And so these are called end games, like from chess. And so one's built out of the Cauchy integral formula, there's another one built out of Puiseux series. These have been around for quite a while, since the 90s or so. And I'm happy to talk more about any of this if any of you want to hear more. That's not always. Okay. If you want to know more, you can always, if you find yourself wanting to solve polynomial systems or wanting to work on this sort of thing, just drop me an email and get Skype. Okay, so let me talk about these few recent techniques. Right, and that'll be most of the talk right there. So, with this first sort of heaviest technique, the Fiberproduct method, Fiberproducts are something from algebraic geometry. The goal of this thing is to identify points in a parameter space we often work over the complex numbers because there are lots of nice theorems over the complex numbers. Complex algebraic geometry, classical algebraic geometry is much nicer than real algebraic geometry. Real algebraic geometry is much more difficult. So we want to identify points in the complex parameter space where the dimension of the, again, complex solution set jumps. And I'll give you an example of that. This is the easiest way to introduce this, I think. So ax squared plus bx plus c equals 0. We want to solve this thing for x. Right? You've probably done this about a bajillion times for different values of a, b, and c. There's a formula out there for it that you've probably heard of. So we have a parameter space made up of a, b, and c. Okay? And we have a variable space, x. Okay? So for different values of a, b, and c, you get different numbers of solutions in x. And of course, the generic number is 2. Right? If I pick a random complex a, and a random complex b, and a random complex c, and I throw them in that equation and I solve it, I'm going to get 2 solutions. Right? Okay. So again, there's sort of this risky open statement there that I could make if I were being more formal with this. Okay, so there are two main cases, I should say. So there are 2 solutions almost everywhere. Counting multiplicity, you could have double roots, of course. Like in the case of 1, 0, 0, right? X squared equals 0, you have a double root. But that's okay, that's still 2 solutions, actually. Sometimes they're real, sometimes they're not. But at the extremely lame point, 0, 0, 0, at the origin, you have 0x squared plus 0x plus 0, right? And there are infinitely many solutions to that. Any x you put in will give you 0. And mathematically, it's not super, well, mathematically it's interesting. Practically speaking, saying that 0 equals 0 is not super exciting. So here's a schematic again. Over a generic point, using that term kind of loosely, there are 2 solutions, but over this one special point in my 3-dimensional parameter space, right? I'm working over C3 as my parameter space. At one point, there's a whole line of solutions. Okay? So, yeah, the dimension of the parameter space is 3. And so, over 3 dimensions in the parameter space, I have 2 points. So you think about moving those 2 points around in 3 dimensions. You end up with 2 3-dimensional sheets that sometimes touch each other at double points. There's 3 2-dimensional things, right? And buried inside them is a 1-dimensional, like a needle, right? Looking for a needle in the haystack. So you could think that maybe these sheets and this needle intersect transversely or something, but in fact, if you do an irreducible decomposition, which is something I haven't really defined, but if you've heard it, you've heard it. If not, it means I'm looking for all the components that are distinct from one another. You won't see the 1-dimensional thing. It's not an irreducible component to the original system. Okay. So the idea then, and this goes back to 2008, it's from Samazi and Wampler, the idea is to take products only in the fiber products, right? I mean, the idea of fiber products goes back much farther than that. But the idea in this particular setting of exceptional mechanisms goes back to 2008. So the idea is, if you take 2 points, you cross it with the same 2 points, you end up with 4 points. If you take a line and you cross it with a line, you end up with a plane, right? So you do one fiber product, and you end up with 4 3-dimensional things when we move those 4 points through 3 dimensions of the parameter space, right? And now our one special point in the parameter space has in fact, it's a plane sitting above it. So we have still these 3-dimensional objects that we don't care about, they're not interesting. But now we have this 2-dimensional thing, which is still buried inside the 3-dimensional stuff, but it's closer to popping out. It's closer to being noticeable. If we take another fiber product, we take those 4 points, and we cross it with those 4 points, we'll end up with 8 points. And, take those 4 points and cross them with our original 2 points, we end up with 8 points. We take our plane and cross it with our original line, sort of in a new direction with a new variable, and you end up with a 3-dimensional thing. And going into, how should I put it? These 8 3-dimensional objects you get from the general points can't possibly include sort of cover up a 3-dimensional object sitting over this point. Once they're the same dimension, one can't be within the other, right? These are both algebraic sets. If they have the same dimension, then it's either the same set or it's a different irreducible component. So at this point, using the techniques from numerical algebraic geometry, you can recognize that there's this 3-dimensional thing sitting there that wasn't sitting there before. We can sort of predict how these should grow. We know two 3-dimensional components should become 4, and then should become 8, right? And so as we're working our way up building these larger systems, through more and more fiber products, we expect to see 8 here, we'd find 9 things. And we can look at them And in fact, this would have a pretty simple structure to it. We'd be able to recognize that that's something new. And we could take it to another level. We could take another fiber product, which means making our polynomial system a little bigger and a few more variables. And we'd end up with 16 three-dimensional blobs that we don't care about, and then a four-dimensional thing. And that four-dimensional thing would be a five-dimensional thing, and so on, as we do more and more fiber products. What this means, though, is for each fiber product, you take your polynomial system and you copy it. And you increase the number of variables. So not the parameters, but the variables, the x's. So the first system had one equation in one variable and 3 parameters, right? And then we take one fiber product, now we have 2 equations and 2 variables, and then 3 equations and 3 variables. And so as you go, I mean, this is a very simple system to start with. You know, as you go, your system gets bigger and bigger. So you don't want to go any farther than you have to. So the key points here are that the fiber dimension increases in a very predictable way. This is sort of a nice thing. So it can help us spot when something new gets promoted up. Notice the dimension over the generic point, the dimension never grew, right? It always stayed a 3-dimensional thing. Whereas the dimension of this thing grew. If the generic point had over it a line, that would grow, or a curve, then that would grow, 1 at a time with the fiber products. It would increase by 1 with each new fiber product. Whereas anything exceptional would have to, by definition of being exceptional, be higher dimensional than that. So it would start out at 2, and then it would grow by 2 with each fiber product. And so eventually it'll pop out. It's a race, and eventually the exceptional points win. Okay, so that's predictable. And also, yeah, exactly, the higher fiber dimensions increase more.
Make this more concrete. I'm
Sure.
a bit lost as to say how you do it actually.
How to actually do it?
Yeah.
Sure.
Let me see the terms just a little bit. Yeah.
So what you do is this. You start with your original polynomial system. X squared plus bx plus c equals 0. And then to go up to the next fiber dimension, let's call this thing x1, you just tack on the same equation again, with the parameters staying the same, but a new copy of the variables.
Okay.
And then if you want to do a third one, you just tack on a third equation with x3.
Okay.
And you just look at the solution sets of those.
And how do you bring it back?
How do you bring it back to?
Well, whatever your problem you're trying to solve.
So ultimately what will come out of this, out of solving this, treating the A's, B's, C's, X's, and x1, x2, and however many x's you have, as all as variables, plugging them into the numerical irreducible decomposition, sort of this fundamental thing in numerical is rate geometry I didn't talk about, it'll find solution sets. And so for this one, it'll find these 4 3-dimensional things. I don't know if I can draw them 3-dimensional looking things, right? So there's components here, and then there's this plane sitting over here. And so what Bertini would spit out is it would say that there are these, in dimension 3, there are 4 components. And you'd expect then when you go up to the third one, where you add in the extra equation and the extra variable, you'd expect there to be these 8 3-dimensional things, but what you see is in dimension 3, then there are 9 components. And so you expected 8, so something new popped out. And so then, that's an indication that there's something interesting happening here. And what you'll get out of this, again, I didn't talk about the numerical irreducible decomposition, but what you get out of this is a point, or at least one point, living on each of these components. And so you'd be able to look at the coordinates of this, and you're, for the one special component, looking at the list of all components, you get something that looks, a special point that looks like 0, 0, 0 for A, B, and C, and then whatever in x1, x2, and x3, some random point on that threefold. And so you would see that when A equals 0, B equals 0, C equals 0, we have something interesting in our parameter space. So that's an interesting point of parameter space.
I guess I don't understand what it means to be 0, 0, 0. You don't have an equation.
You do. It's sort of vacuous, right? So, yeah, so at that, so how many solutions are there for what x does a squared plus b squared plus c equal 0 if I plug in 0, 0, 0 for a, b, and c? There are infinitely many solutions.
Right. Why aren't you interested in 0, 1, 1, for instance? I mean, if A equals 0, but B is still not 0.
Yep.
I thought that would be more interesting.
Not interesting. It's interesting in a different way. But our method will pick out things where the solution set's dimension is higher. So, so this technique wouldn't apply for finding that, because there's going to be one solution instead of two. So, so the generic fiber there is just, it's just 1 point instead of 2 points. But it's going to still be a measure 0 set downstairs, right? Because you've set A to be 0. So you've already made that an algebraic set in the parameter space. So it's already a lower, it's a measure 0 set of the parameter space. So yes, that is an interesting thing. And so it'd be nice to have that software from the first slide where you can plug that question in, but this technique wouldn't solve that problem. So I can't find every point of interest. I can't, for example, with Fiberproduct methods, find where there are two real solutions instead of the two solutions being complex or mixed. All Fiberproducts will find for you is when you have this positive dimensional solution set over a particular subset of the parameter space. Does that make sense? Okay. Yeah. Anything else on this? I don't want to run over. Is it 50 minutes or an hour? Hopefully not 2 hours. We have an algebra seminar at CSU that's 2 hours. Yeah, I just had this slight fear in the back of my mind that maybe this was meant to be 2 hours. In which case I could slow down a lot. I won't go that long. So
the camera is still pointing to
the
board.
Thank you. Okay, thanks. So, yes, the current status is that there was this paper in 2008 with this algorithm. In fact, the paper was probably written a few years before that. And just implementing it in the simplest way that we can, just doing some runs in the Bertini software package. You can solve something for two-link mechanisms, maybe a little bit larger than that. But even something called a planar pentad, I'm guessing there probably aren't kinematicians in the room. So, okay, solving still fairly a simple problem called a planar pentad. This computation is too hard using Bertini 1. So there's a small team, including one of my former students, Eric Hansen, John Honstein, who you saw several weeks ago, and one of his students, Alan Liddell, and the guy from General Motors, Charles Wampler. We're looking at making algorithmic improvements on this. So as you add in more and more equations, one way to solve the new system is to just start from scratch. Pretend you didn't solve any of the previous systems. So when I go to the 3-fiber product system from the 2-fiber product system, I can not think about the 2-fiber product system and just start Bertini out from scratch, build a start system and go through everything. There's a more intelligent thing you can do called regeneration, where you take the solution set of the 2-variable 2-equation system, and then you can sort of morph in the third system. Well, that's not really the point of this talk, but I can tell you more about it sometime if you want. And so we're using that, and we're using some other newer bells and whistles that have come out in the last 10 years or so to try and speed this computation up. And the reality is it's still not an easy computation, but we're also looking for something that people haven't been able to find except sort of through luck or other more difficult computations. There aren't a lot of examples of exceptional mechanisms out there. There are classes that people use all the time, mechanical classes that people use all the time, where they have no idea if they're exceptional mechanisms. So, right. Okay, we'll get there. Hopefully. Okay, so that's one kind of parameter space technique. Another one is if you're looking to find points in the parameter space. So you think about maybe just some Euclidean space, some maybe 3-dimensional real space. Suppose you can move around in that parameter space at different points in that parameter space, plugged in, just like we plugged in A, B, and C into our original equation from the quadratic formula example. So when you plug those in, you'll get some number of solutions, right? So we want to move around and try and find where there are the most possible solutions. So can we realize some point in parameter space where you have the maximal number of real solutions? Okay. The idea comes from Dietmeier. He used a different computational technique, not homotopy, something a little bit different, but the idea is there are these borders between chambers. And what is a chamber? It's a set of all points where you have the same number of real solutions. And the locus, the discriminant locus, is where you move through this. Or you move through the discriminant locus to move from one chamber to another. So you'll get possibly more or possibly fewer solutions as you move through the discriminant locus. And so Dietmeyer's idea is find the nearest point on the discriminant locus and just blast through it, and then you're in a different chamber. Maybe there are more real solutions, maybe there are fewer, but that's a way to at least sort of wander around in this parameter space and try and find some things. And Griffin and Honstein took that idea and built it into a homotopy so that, which works a little more nicely around the discriminant locus in particular. So the idea is this: suppose this is your discriminant locus and you're at this red point right here. You'd find the nearest point on the discriminant locus and just draw a little line segment and then just march through the discriminant locus to the other side. That's what it boils down to. Given the amount of time I have left, that's about all I want to say about it other than this. So here's our discriminant locus. Again, this is sort of a schematic drawing. Here's a discriminant locus. We're moving from point 1 over to point 2, P1 to P2. We have 4 complex solutions over there. And the hope is when you cross a discriminant locus, you'll end up with 2 complex and 2 real. The complex conjugates will run into each other and split off into 2 real, for example. So it could be, though, that if you were going from P2 to P1, you might have 2 real solutions and then you end up with 4 complex. I mean, just walking through the discriminant locus blindly isn't necessarily the right thing to do. The difficulty, too, is if you're at a particular point and you want to try and turn it into a real point, I mean, walking across this piece of the discriminant locus right here, for this point, does you absolutely no good, because that piece of the discriminant locus is there because of these 2 points turning real, not because of that point turning real, right? And so somehow it matters which path you're on if you're following particular paths. So current stats, so there's this one paper on this. I think it's a cool idea to try and investigate parameter spaces, but I think it hasn't been, having talked to John a year ago, it hasn't been used a lot outside of these couple of problems. They sort of resolved the Steiner and Stewart-Goff problems using this technique. And again, having many points in the fiber. So say you have 1 million points in the fiber over a particular point in the parameter space, and you take one of them and move them across a discriminant locus. I mean, it's, well, I guess, 2 in a million chance that you pick one of them that actually will change to real. So it'd be nice to have something like a branch-specific discriminant locus. But that's something that I don't know anything about. And if you do, I'd like to know more. Okay. And then the last topic, maybe we have 7 minutes or so left for questions, is parametopy. So when I realized that these parameter space problems were of interest, I realized that at the same time that running Bertini over and over and over on the same problem, I mean, I could write down a problem and just change the coefficients from one run to the next. Redoing that, over and over, it takes it just wastes a ton of time, because you're always parsing in the polynomial system, and solving a system from scratch is often less efficient than solving the system based on a system that you've already solved, for reasons I'll get into in a few minutes. So I recruited a couple of students, Matt Niemerg and Dan Brake, and the 3 of us together worked on building parametopy, parameter for parameter homotopies. It used to be called Polysaurus. I put my foot down so we can't call it Polysaurus for some reason. It just didn't sound professional. So now we have parametopy. Okay, and it uses parameter homotopies, which are like cheater's homotopies if you've been around for a while and know that term. And it relies on Bertini as a computational engine, but it doesn't use Bertini as a black box. It actually connects on the inside of Bertini. It makes calls as if Bertini were a library, which it generally isn't yet. So here's the idea. If you have some parameter space, and these Q's live inside this parameter space, and you have certain points that you care about in your parameter space. So I've sort of taken a mesh. You can think of this sort of in R2. Maybe it's actually a 3-dimensional parameter space. We can pick some random point in that parameter space, plug those values for that point in parameter space into our polynomial system. Sorry, that's my generic polynomial system now. So plug them in and solve that from scratch, right? Maybe you follow 1,000 paths and there are only 7 solutions. Since it's a random point, you're probably in the Zariski open set that has the maximum number of complex solutions. So any of these points, unless you're extraordinarily unlucky, meaning you play the lottery, win the lottery and get hit by lightning on the same day, and it's even more serious than that. Unless you're extremely unlucky, the number of solutions here will be the same as the number of solutions for each of these points downstairs. And so we follow 1,000 paths to solve that problem, this random problem first, and then we move from the random problem to each of the problems we care about following only 7 paths, right? And so we have 0.7% the work that we had to solve the first problem. You could solve each of these problems independently if you wanted to, but then you follow 1,000 paths into each one, and that's just a huge waste. Okay? So you could do that in Bertini or in PHCPack or in Hom4PS. These are other continuators, other software packages. Something that we built into Parametopy is if you get path failures, suppose we walk near a singularity as you're walking from Q prime to some of these points, and some of your paths get too close to other paths, and we increase precision, and cut step length, and tighten up as much as we can, and then finally we hit our thresholds and say we're not going above 300 digits. We're not going to make our step length smaller than something. Then we'll kill those paths, and so you can have failures walking along some of these arrows. And then what Parametopy will do, it'll query if you want to do this. So we'll move to a different point and try and come into it from a different angle. Try and come into those difficult points in parameter space from a different angle. It doesn't sound like a very exciting thing. In fact, it's not a very exciting thing. But you couldn't do it before. It's an icon. And so it's a software solution. So here's what a Parametopy input file looks like. This is not far from a Bertini input file, and I'm not going to walk through the whole thing. We have a polynomial system, and you have some parameter values you care about that are fixed. And then there's some parameter values that you care about that are not fixed, and you can specify, in this case, a grid. This is saying, please grid up 0 to 1 in K4 and 0 to 1 in K2 with 40 mesh points one way and 50 the other way. And then you feed this into Parametopy. It uses all the nodes that you tell it to use, and it just churns away and does this parameter Hometo stuff. Okay? And then collects data. We have some MATLAB files that collect and massage output for you. There are all sorts of things that are configurable. I'm not trying to sell this to you. If you want to buy it, it's free, so it's not the sort of thing you can make much money on. But it's out there if you want to solve parameterized polynomial systems. You can collect lots of data. And yeah, if there are any failed paths, if anything goes wrong with the run, this will collect information and tell you about it. Then you have options like rerunning failed paths from a different point. Okay, so it exists. It's out there. Working with Dan Brake and I are working with some people from Harvard Medical School and solving some reaction network problems, chemical reaction network problems that they've come up with, and I'm trying to collect some statistics about where these regions are that have multiple stable points. And then coming up, we're going to move this Parametopy and other software packages into sort of the Bertini sphere. Right now, it uses Bertini as a black box, and that's not necessarily the right way to. Well, not quite as a black box. This is a little more sophisticated. It's not quite the right paradigm. So, okay. So Bertini 2 update. This will just take a couple of minutes for those of you who've seen Bertini before. If not, maybe you've seen software before. Well, I guess probably everybody's seen software before. Maybe you work on software. So this is what we're going through. These are the growing pains we're going through right now in the Bertini group. And then, yeah, one more slide at the very end. So Bertini. This is what I worked on as a grad student. I finished it up in 2006. John Honstein came on board a little bit before then. And Andrew Samazi and Charles Wampler, the four of us are now, we're the core development team until we added Dan Brake about a year ago. So we're up to version 1.5, which again doesn't sound so exciting, but when you start with alpha and then go to beta and then 0 and then 1, and then it sounds a little better. So it has various techniques available. It's been used by a few hundred people for various sorts of problems. A lot of them from applications, but also some algebraic geometers. There's some decent artificial intelligence for some tolerances. And it's okay as a black box, but there's not enough artificial intelligence to make it a really good black box yet, where you can just drop a problem in and trust you're going to get good answers out. Luckily, it tells you if you're not getting good answers. It tells you if something broke. So that's better than getting answers out that you don't know if you can trust or not. That would be worse. Cons, it's a very small development team. Only 2 people are active in it right now. It's legacy code. People don't want to dig in. So if you've been around software, you know this happens eventually. People who wrote it know what's in there. Eventually they sort of go away or don't have time for coding. Like I don't get my hands dirty and code much anymore. And so now Dan Brake's learning the ropes, and it's painful to try and pick up somebody else's code and mess with it. There are many layers to the onion. Maintenance and extension are hard. I mentioned it to you earlier. There are these 3 versions of everything. If you change one, you have to remember to change the other 2, and sometimes we don't remember. That's not good. Many special versions and Easter eggs. People say, hey, could you compute this? And we say, well, not exactly, but if I tweak the code, and so then we just spin off an Easter egg, or we spin off a special version for that person. And occasionally we make some tolerance. If you want to run Bertini in that mode, you have to set some tolerance to -47 or something. And if you happen to set it to -47, then it'll do this, this unexpected behavior. So lots of Easter eggs. I know what you guys are going to do with your time now over the weekend. Go code, trying to find all the Easter eggs in Bertini. The source code's available, so it's actually kind of easy to find them. Their license is super restrictive on Bertini 1. There's no scripting, no access to sub-algorithms, no nothing. Everything's closed. And everything used Bertini as a black box. So Bertini sat in the middle. It connects to R, MATLAB, Macaulay 2, and Cocoa, and has lots of children, lots of modules that depend on it and use it. Generally, is a black box. And there's some related software on the side for certification also, Alpha Certified and Cadenza. So it's sort of its own thing, and people can only touch it, from the outside. And yeah, there isn't really time to talk about those particular things, unfortunately. So Bertini Classic is difficult to maintain and extend, so we're rebooting, we're writing it in C++. We have this new NSF grant to redevelop Bertini in C++. Everything is open source, GPL, version 3. It's on GitHub, you can go look at it right now if you want to. We do automated testing, it's set up daily with Jenkins, and so this is software it's like a cron job. It'll run your software every day on a test suite. And so there's a fixed review process for the core and for the modules, so several people put eyes on every bit of code that goes in and on all the tests that get built. Every time you build a little piece of the software, you have to build a bunch of tests that test the spectrum of things that software or that little piece is supposed to do. We're making it all available as a library instead of having it as a black box thing. So if you compile your own code, you can link in our library, and then you can just call our routines instead of having to touch it from the outside, which is harder. There's a Python interface, it'll be interactive. The thing I'm most excited about is a credit generator after you do a computation. We haven't built this yet, but we have plans for doing it, and we promised we'd do it in the grant, so now we have to do it. So after you do a computation, you can say, please tell me what papers were used in the algorithms, where the algorithms were developed for the computation I just did. And so it'll just spit out a little bibtec file for you, and you can just copy and do your references. So this is always a problem with software. People do some sophisticated computations, somebody spent a long time building an algorithm and implementing it, and then they cite the software where it's implemented. And that's really frustrating for the people who build the algorithm. So we're trying to do something about that, at least with Bertini. And we're going to have workshops for novices, and also, so if you want to learn something about numerical algebraic geometry or about using Bertini, or if you want to develop modules, if you're a little bit beyond being a novice, that's also part of the point for these workshops. So the idea is to take this picture and turn it into this picture where this is Bertini, and it has all these other libraries inside. There's some core methods, and we're almost done building those now. There are connections out still, and there's some unsupported modules. So things are more inside the sphere. They can connect more deeply to Bertini. Okay, and actually it'd be good to talk about this very briefly, and then I'll be done. If you want to learn more about Bertini, there's a workshop, our first workshop actually. So you can be a guinea pig. It'll be in South Bend, Indiana in May. I watched part of John Hanstein's talk a couple days ago, and he said there's a direct flight from Newark to South Bend. So if that's a selling point for you, I guess there's probably a direct flight from somewhere in New York to anywhere. So maybe it's not saying much. But anyway, that's coming up in a couple of months if you're interested. It'll only be a few days, so it's hopefully not too much of a time commitment. There'll be a summer school in applied algebraic geometry, including a second workshop in Rome. In 2018, Notre Dame has a campus next to the Coliseum, because they're Notre Dame. CSU does not have a campus next to the Coliseum, as it turns out. I checked. So ICERM up in Providence is going to have a special semester on nonlinear algebra. A lot of numerical algebraic geometers and other flavors of algebraic geometers, and other flavors of numerical people will be up there in fall 2018. So that's this is sort of a satellite to that special semester. And there's also a new journal. If you're in the community, you probably already heard about it. A new SIAM journal, SIAGA, SIAGA maybe. That starts accepting submissions next Wednesday, so a week from yesterday. So if you work in this field, that might be good for you. Okay, and in fact, that's a Stewart-Goff mechanism right there. Charles made that picture. Okay, and that's it. Thank you. So any questions? Yeah.
Can you re-explain how you find the smart paths in the discriminant space?
So, yeah, what makes the paths smart is, you could start somewhere where you have in your fiber, let's just say 40
Can you explain this picture?
complex solutions. Yeah, this picture is, you can think of this as a discriminant locus, so it'll be different numbers of real solutions. So think of this as a parameter space. Well, either one of these are two separate pictures. So this is a parameter space, and the number of real solutions is different inside the different chambers. Okay, so there'll be, I don't know what the numbers are for these examples. I have to go back and look at the paper, but maybe five real solutions here, and 2 real solutions there, and no real solutions there, just to throw some numbers out there. And the idea is, to find all the different chambers, you could just take a point and just meander around through parameter space and just see when you happen to have a different number of real solutions. But instead, what makes the path smart is you do a computation. Sorry, I'm trying not to get my shadow in the way. So if you're sitting at this point, you do some computation. You find the distance from this point, the shortest distance from this point to the discriminant locus. And it'll spit out that point on the discriminant locus. And so what you do is you just move from that point through the discriminant locus into the next chamber. And of course, if that chamber is very small and you move too far past the discriminant locus and you've actually moved all the way through that chamber and missed it. So I mean, it's a heuristic. There are still some issues that need to be worked out. But the point is then, as you move through, you go from having 5 real solutions. Okay, the numbers I chose were bad. 5 real solutions to, say, 3 real solutions, because 2 of them came together and turned into complex conjugate. So that's a picture of you can think of that as a discriminant locus.
How do you get the closest point on the discriminant?
So you could write down an optimization problem, and the problem is to minimize the distance such that, so you want to minimize the distance from this point to XYZ such that XYZ sits, well I guess here XY sits on the discriminant locus. And so you could write down the equations for the discriminant locus. And so, and then when you write down the optimization problem, you can use something like Fritz-John conditions or Krush-Tucker conditions, KKT, to turn it into a polynomial system. So it's all a polynomial system. And that'll give you the nearest and the farthest. So if you're sitting here, you'll pick up not just that point, but you also pick up that point. And you might even pick up, if there are points that are solutions of the, that are minima of the distance function, you might pick up points on other pieces too. But then you can figure out which one's the closest just by figuring out the distance. That's an easy computation. Does that answer your question?
Yeah.
Okay.
So how big a system can you solve?
Just from scratch, right? Not with this in particular, but you're saying just in Bertini, you're just dropping it in. So there are 2 answers. One, if you want to find all points and curves and surfaces and all higher dimensional things, a few dozen variables. If you want to just find all solutions, we've gotten up to about 100 variables, but that's for a very low degree system. So I'm sure you know this, but for others who don't, well, maybe I won't even write it down. If you take the degrees of all of the equations and you multiply them together, that gives you what's called a Bézier number, and that's an upper bound on the number of solutions that you can have in a polynomial system. And so the size of the system has to be measured both, in variables and also in degrees. And so, if we have even for the 100 variable system, it could be that some of them were linear, because even to have 2 to the 100 solutions would be way too many to track. That's impossible. So it couldn't have been a system of quadratics. However, the Bézier number is just sort of the first approximation, first upper bound, the loosest usually upper bound that you can get on the number of solutions. You can do multi-homogeneous root counts and other root counts that can decrease that. And so it depends on the structure of the system, is what I'm trying to get at.
I mean, 100 is very impressive. I mean,
yeah.
I guess in computer algebra, typically 5 by 5 systems already choked.
Right. And in my experience with
even quadratic 5 by 5 system
with quadratics,
kills it.
With that, so for that, I'm comfortable going up to 10 or 15 variables with quadratic systems. That's not too bad generally. It depends on the structure a lot, and it's the same as in the symbolic world. If the problem has special structure that you can somehow exploit, then you can take advantage of that. It's just the structures that are useful here are different than the structures that are useful for symbolic methods. And also, it's maybe worth noting, in my experience, there's this paper that the Bertini and Singular teams wrote together a few years ago. It looks like symbolic methods scale much better with higher degree and fewer variables, whereas numerical methods scale much better with more variables but lower degree. And so if you have a very high variable system, high dimensional system but with low degree, numerics are the way to go. But if it's squished the other way, then symbolics are kind of the way to go. And exactly where that line falls, I don't know. It's hard to find good. You know, if you take all the benchmarks that are out there, all the polynomial systems, it's still just a smattering of systems. So it's hard to generalize too much. Yeah. Other questions?